My name is Bruce Director. When you look at the motion of the sun, the stars, the planets, and the other heavenly bodies, do you know the physical causes that underlie such motions? Or are you like most people, ignorant of the true physical causes and dependent on what you heard from teachers or read in textbooks for your knowledge of the physical universe? The following presentation is intended to acquaint you with the key concepts and experimental material that underlie the discovery of the principles of universal gravitation that were made by Johannes Kepler in 1609, and the discovery of the path of least time that was made by Pierre de Fermat shortly after. It was inspired by Lyndon H. LaRouche, Jr., who is today the world's leading authority on the science of physical economy. LaRouche has frequently cited these two discoveries as exemplary of the kind of scientific method that one needs to know in order to gain a competent understanding of the principles of economic policymaking. Unfortunately, most people today are completely ignorant of these discoveries. Even specialists in physical science know little of the original discoveries and instead are willing to repeat gossip they heard from their teachers or read in lying textbooks, rather than having relived the discoveries for themselves and be able to reproduce them as if they were original to them. Consequently, what I have done is attempted to present to you pedagogically, using computer-generated star charts and animated graphics, the basic material experimentally and the basic concepts that underlie Kepler's and Fermat's discovery. Much of the material was presented at a conference in February of 2001 sponsored by the Schiller Institute held in Reston, Virginia. I have supplemented that material and will interrupt the presentation at several points in order to present to you additional evidence that was put together here in the studio. Most of the material is completely elementary. All that is required is your concentration. Over the next hour or so, I wish to activate your imagination to help you accompany me along a journey of discovery that will begin today, but hopefully will continue long after we've left this room. Our guide for this journey will be Johannes Kepler. Kepler was a revolutionary scientific thinker who lived in a time not unlike our own, in which the world was in a fairly pitiable state. And it is indisputable that every accomplishment in science since is based on Kepler's work. And for that reason, he's a fitting guide for our journey. Now, before commencing on this journey, you can't go on it unless you give up your commonplace notions of space and time. And for that, I'll have to ask you to perform a certain experiment to help you recognize the fallacy of these common sense notions. Let me ask you first to look up to the ceiling. Well, before you do that, let me ask you to think about the question: what is the shape of the space in this room? Now, it would probably not be presumptuous of me to assume that you probably answered that question rectangular or cubical. Now I'd like you to look upward and find a spot on the ceiling directly above your head and point to that spot. Point to it, yeah. Now I'd like you to point to a spot directly above my head. I've illustrated it with a laser light. Okay? Now point back to the spot above your head. And point to the spot above my head. Now, ask yourself, what is the connection between those 2 points? If you say a straight line, you have just identified a fallacy in your own commonplace notions of space. Because if you think about the action of your arm moving from the spot above your head to the spot above my head, your arm traced out the arc of a circle. And in fact, all sense perception, all vision, regardless of what ivory tower notion you impose on it, is bounded on the surface of a sphere. And that the idea that this space in this room is somehow linearly extended in 3 directions, or somehow a space of Euclidean matrix, is just an illusion. Your notion of space, the manifold of measurement of action, is the inside of the surface of a sphere. And no matter how hard you try, all your visual perceptions are bounded on the inside of the surface of a sphere. And the farther objects get away from you, the more this becomes evident. Now, we also have to give up our commonplace notions of time. Now, if I were to ask you what time the sun came up this morning, some of you may know, if you were up that early. If you weren't, you know, you might, the time, at least as reported, was 6:58 in the morning. But how about if I were to ask you, what time was it when your watch pointed to 6:58? Do you have trouble with that question? Does it sound funny to you? Why do you consider the rotation of the hands on your clock's face to be something more absolute than the motion of the sun? Why is it easier for you to measure the sun by your watch than to measure your watch by the sun? And in fact, time is not an absolute quantity that your watch measures. Time is the juxtaposition of different cycles. And if you take these, if you leave your commonplace notions of space and time at the door, and you recognize what I just said, you're ready to go on this journey. I might point out to you that you should realize by this that it's useful to look up every once in a while. You usually find out something that you didn't previously know. Now let's go to the next slide. When we're looking at the heavens, because we recognize now that all the observations that we see are on the inside of a sphere, all we know, all that is directly observable, are changes in position of the stars and the other heavenly bodies on the inside of a sphere. And that sphere is known as a celestial sphere, and everything is measured only by 2 angles, an angle along the horizon and an angle up above the horizon. So everything we're going to look at are representations of changes of position of the heavenly bodies on the inside of this sphere, which is the only aspect of the motions of the planets that is accessible to your vision. Now, the first obvious recognizable cycle in this respect is the daily cycle of the sun across the sky, which I don't need to illustrate because you're all very familiar with it. The sun, as you know, rises in the east, traverses an arc across the sky, and sets in the west. And you're all very familiar with that. Now, let's go to the next slide. Now, there's another cycle which you may or may not be familiar with, which is the nightly cycle of the stars across the sky. Now, this is a representation of what the sky will look like tonight from this location on Earth that we're at after the sun goes down. It is a projection onto the flat surface of the celestial sphere that we illustrated before. The yellow circle would be the horizon. You can imagine if you were lying on your back, looking straight up. The center of the circle would be right above your head. And the yellow circle around it would be the horizon. You see the stars in the sky, and these red dots down here are 3 planets, Venus, Saturn, and Jupiter, which will be easily visible to you right after sunset. Now let's run through this sequence of slides, maps, projections of this at 10-minute intervals over the course of the night. And you can see that all the stars rotate in a circular path. Here's the Big Dipper rotating around in a circular path over the course of the night. You should also notice that there's one star, this one here, which doesn't seem to move at all. And that star is the pole star. Now, for the Aussies in the room, this may look even more unfamiliar to you. But don't feel bad, because it's probably unfamiliar to many people who haven't even bothered to look up in the night sky themselves. And now the sun has come up and the cycle is over, at least for that night. So now we have 2 cycles that are listed. One is we'll start listing the various cycles as we discover them. One is the daily cycle of the sun across the sky in a circular arc, which is a circular cycle. And the second is the nightly circular cycle, apparently circular cycle, of the stars over the course of the night. Now, let's move on to another cycle. Let's have the next slide. Before continuing with the presentation, let me interrupt for a moment and describe the perspective of the next series of slides. In this picture, imagine you are looking due east. The arrow points out the position of the sun. To the left of your screen is towards the north. To your right is towards the south. And behind you is west. The yellow line is the horizon. What you see here below the yellow line would be beneath the horizon and not visible to you from your position on the surface of the Earth. This is a depiction of the sunrise on the vernal equinox. And that's the day that the sun rises due east. And the sun is just poking over the horizon. And behind the sun is the background of stars. And this particular configuration of stars that I'm pointing to there is known as the constellation Pisces, the fish. This pentagonal shape there is the head. Then you have the body and the tail of the fish. Now let's go to the next one. I've put in the lines here so that you can see, for purposes of illustration. Obviously, when you go out and look at the night sky, God didn't draw lines between the stars. But since we're using computers here, we have to dumb it down a little bit, at least for this purposes. Now, what I want to do is run through a sequence of images that show you the changes that show you the changes in the position of the sun and the stars at sunrise, first at daily intervals, and then at 20-day intervals. So why don't we run through that? There's a little close-up so you can see Pisces there. Go ahead. And you can see that these are daily intervals, that each day the sun rises a little bit further to the north of east. And when it rises, it's the constellation Pisces is a little bit higher up in the sky by the time the sun rises. So there's two movements here. One is the sun along the horizon towards the north, and the other is the constellation Pisces moving higher and higher in the sky at sunrise. Now we've just jumped 20 intervals, so we can see 20-day intervals, so we can see the whole year. So go ahead, and you see that each 20 days, a new constellation, or 30 days, a new constellation is behind the sun, and the sun now, having reached a high point in the northeast, is now starting to move back towards the east. And now it's starting to move towards the south, and it will reach an extreme point in the south and move back towards the east again. And if you will notice that when it gets back to due east, Pisces is back in the sky at what appears to be the same position that it was the year before on the vernal equinox. However, as you'll see in a moment, it's not exactly the same position. So let's go to the next one and just list so we don't lose track of these things. We have the 4 cycles now, which we've observed. One is the daily cycle of the sun across the sky, the nightly cycle of the stars around the sky, the cycle of the sun's position along the horizon from east to north to southeast, back to east again. That's called the tropical year. And the motion of the cycle of the constellations that rise with the sun over the course of the year, which is called the sidereal year. Now, as I said, even though it appeared that we came back, that these 2 cycles came back to the same place, there was a slight difference between the 2 risings at the vernal equinox over the course of a year. Let's go to the next one. This is what the sunrise on the vernal equinox looked like in the year 1, 2,000 years ago. Now notice that Pisces is much higher in the sky, but the sun is due east. The sun is exactly due east, but when the sun was due east 2,000 years ago, Pisces was high in the sky. Go to the next one. This is this year's vernal equinox, and you see that Pisces is lower in the sky. Switch back so people can see that. This is 2,000 years ago. This is today. So even though on a year-to-year basis, the difference between the tropical year and the sidereal year seems to be imperceptible, which a baby boomer would gladly ignore. Over 2,000 years, much longer than most baby boomers think, it makes a big difference. And in fact, it takes 77 years for this cycle to progress 1 degree. And it takes approximately 25,000 years to go through the whole cycle. Now, you go to the next slide, we list now the 5 cycles that we've discovered: the daily cycle of the sun across the sky, the nightly cycle around the sky, the tropical year, the sidereal year, and the 25,000-year cycle of the precession of the equinoxes. Let's go to the next one. This is a metaphorical depiction of those cycles as viewed from the shortest cycle to the longest. That is, the sun moving across the sky over the course of the day is the shortest cycle. The cycle along the horizon from east to north to south and back to east again is the next longest. And then if you can imagine that dome turning slowly on a 25,000-year time scale, that is the longest cycle. Now go to the next one. This is a depiction of exactly the opposite version, going from the longest to the shortest. If you look at the entire torus, that represents the 25,000-year cycle. Each loop represents 1 year. It's a spiral loop, so you have 25,000 spirals going around. And if you look closely at the spirals, these are not just lines, but they are cycloids, epicycloids, and there are little bumps there. And each bump is 1 day. So you have 365 bumps in each loop. You got 25,000 loops in one torus. And I'll let you in on a little secret, is that even the precession of the equinox doesn't come back to the same place. So instead of that torus actually closing, it should form another spiral, which then forms another spiral and another spiral. But the important thing for us, right, to keep in mind is that at every small interval of the planet's motion across the sky during the course of the day, the longer cycles are just as much present as the shorter ones. And that's depicted in this extreme close-up, in which as the sun moves across the sky in the course of the day, it's also moving along the torus in its yearly loop, and along the axis of the torus in the equinoctial cycle. So at every small interval of the sun's motion that you see, all those cycles are operating, even if they seem to be beyond your capacity of measurement at the time, but they are all at work at every moment, at each single moment of the sun's action. Not only are these cycles not commensurable with each other, that is, they all don't close, but there's something also that's can be very disturbing to people, which is that they are non-uniform cycles. This is a picture of where the sun will rise on June 21st. Go to the next one. That's sunrise on July 23rd, 31 days later. This purple line here is the ecliptic line, that is the path that's on which the sun moves against the background of fixed stars. You can see the distance along the zodiac that the sun moved in that 31-day interval. Now go to the next one, and now I have both positions, June 21st and July 23rd, marked up here. Go to the next one. And the distance the sun moved along the zodiac in that 31-day period was approximately 30 degrees. Now this is sunrise on December 21st. And go to the next one. That's the sunrise on January 22nd, 31 days after that. Go to the next one. This is both of them together, and the purple bar there marks the 30-degree mark from the December 21st rising. And you can see that the sun has traveled more than 30 degrees in 31 days. That is, when you compare the daily cycle of the sun to the yearly cycle, not only do they not come back to the same starting place, but it doesn't move uniformly. Let's go to the next one. I have a close-up of that. So you can see this little distance here. In fact, the sun moved nearly 32 degrees through the zodiac during that 30-day period. Go to the next one. Now we'll go through the whole year. This is sunrise on July 4th. Go to the next one. This is 31 days later. The sun has moved approximately 30 degrees. Go to the next one. And the sun now has moved, if you notice, the purple mark there is the position that is 30 degrees from where the sun was 31 days earlier. Go to the next one. Next. You see, as in each 31-day interval, the sun is starting to move a little bit more than 30 degrees till we get to December, and the sun has moved 32 degrees, and now it starts to move a little less than 32 degrees back to 30 degrees in 31 days. In other words, the sun moves faster through the zodiac in the wintertime than it does in the summertime. And it is always either speeding up or slowing down. It is never going at a uniform rate. So now let's go to the next one, which are the cycles of the planets. Which to view these, I decided it would be good to look at where the planets were in 1580. This is what the sky looked like from Prague on the night of August 22nd, 1580. The purple arrow points out the position of Mars, and the red arrow points out the position of a very bright star in the sky called Aldebaran. The constellation that Aldebaran is in along the zodiac is known as Taurus, the bull. So that's where what the sky looked like if you were in Kepler's shoes on August 22nd, 1580. Now, let's see where it was 10 days after that. You see that Mars has moved relative to Aldebaran and the constellation Taurus a little bit to the east. In the same way the sun moved through the constellations from west to east. Go ahead, next one. These are 10-day intervals, next one. And you can see that Mars is moving a little bit to the east on each day. Keep going. And now you see something funny happening. Mars is starting to move backwards from west to east. And these are 10-day intervals. Of course, you look at it on a daily basis, it would be smaller changes, but nevertheless discernible that Mars would be moving backwards. And then Mars decides it's going to move forward again, moving back again west to east, and over a 10-day interval. And it keeps moving to the west until it continues its path. Now, let's do that sequence again, and what I've done here is left each position on the screen so you can actually get a better sense of this loop. Go ahead. This is August 22nd. There's 10 days later. Keep going. Each arrow represents a 10-day interval, and you can see how Mars starts to go backwards and makes an actual loop in the sky. Now, of course, August 1580 was not the first time Mars did this. It happens all the time. The ancients have looked up to this. All people have looked up to this. This is Mars in 1582. And you see that it's come back to the same place in the zodiac. Remember, the last sequence we saw, Mars went off around the zodiac again. This is almost 2 years later, not quite. And Mars has come back to the same place in the sky. And this is in November of 1582. And Mars is in a completely different place in the sky. This is a totally different position, constellations behind it. And let's go to the next one. And you see that Mars is moving west to east, but keep going. But Mars has decided also, at this time, now it makes another loop, but it makes that loop in a different place in the sky than it did last time. Now, Mars also, like the Sun, moves across the sky moves through the zodiac at a non-uniform rate. This is Mars on April 4th, 1580. Go to the next one. This is 30 days later, and Mars has moved approximately 22 degrees along the ecliptic through the zodiac. The yellow bars are the positions of, represent 22 degrees from the last rising, and the purple arrows point out the position of Mars. Go to the next one. Now, you can see that Mars, in this 30-day interval, has moved a little bit less than 22 degrees. Go about 21 degrees. Go to the next one. And in this 30-day interval, it's moved about 20 degrees. Go to the next one. All right, now here's Mars in 1581. Go to the next one. In a 30-day interval, at this place in Mars's orbit, Mars has moved only 14 degrees during a 30-day interval of a period. Now, when I speak of 30 days, don't remember what we said earlier about the relationship of time, that it's not, I'm not talking about 30 days of your clock. I'm talking about 30 rotations of the Earth, or 30, don't even think of it as rotations of the Earth, think about it as 30 cycles of the sun across the sky. In 30 cycles of the sun across the sky, Mars moved here only 14 degrees in the zodiac. Next one. In this 30-day period, it's moved about 16 degrees. And in the next one, it's moved about 17 degrees. So Mars, like the Sun, speeds up and slows down in its course through the zodiac, and it also makes these loops. And as it speeds up and slows down, it's never moving at a uniform rate, and it makes these loops at different parts in the sky. So go to the next one. So these are the cycles which we've so far discovered. One is you have the cycle of the sun across the sky in the day, the nightly cycle of the stars, the tropical year, the cycle of the sun along the horizon, the sidereal year, the cycle of the sun through the zodiac, the precession of the equinoxes. Go ahead. The cycle of Mars from one retrograde motion to the next. When Mars starts to go backwards is called retrograde motion. You can call it loop-de-loop. And the next cycle is the cycle of Mars through the zodiac, where it comes back to the same place in the sky. So we have all these cycles are at work, are as known to you by changes of position on the inside of a sphere. That's what you know about the motions of the planets. Let's go to the next one. This is a drawing that Kepler made of the motions of Mars that was published in his groundbreaking work, The New Astronomy. And you can see his depiction shows the very, very irregular patterns. Now, how you understand these complicated motions on the inside of a sphere of the heavens has as much to do with what's in your mind as it does with what's in the stars. There are two views of this, two diametrically opposed views, which correspond to two diametrically opposed views of man. One is the view associated with Babylon, the Roman Empire, the feudalist order, that these complicated motions of the skies are beyond human comprehension to be able to actually know what the causes are. That these are, in effect, irrational motions. And only a small group of priest class, or today we would call them mathematicians, can tell us how these motions, or what is governing these motions. And the majority of people are unable to grasp these seemingly irrational motions, and therefore have to rely on this class of astrologers, mathematicians, oligarchs, who know the secret knowledge of how the planets move and so forth. And by propitiating the potentates, one who know this secret knowledge, you can bring these irrational forces to your aid as opposed to your detriment. And of course, this is the way it's done. In the Babylonian times, the tax collector was the guy who knew when Mars was going to be in a certain position, because that was the time when you had to pay your taxes to him. The other view is the view that has existed for as long as man has been man. But much of the history, of course, is not known to us. But it comes down to us primarily through the work of through the writings of the Egyptians, and most importantly, the Greeks, the classical Greek scientists and scholars, who understood that that what we can know with our mind, what we can't know with our eyes. And that man's mind is capable of taking these complicated motions and bringing them into an order so that man can know, any human being can know, through the power of cognition, how God ordered the universe to produce this beautiful dance of the heavens that we see over the course of the night. Now, in his New Astronomy, Johannes Kepler, in the very beginning of the first chapter, described this process.
The testimony of the ages confirms that the motions of the planets are orbicular. It is an immediate presumption of reason, reflected in experience, that their gyrations are perfect circles. For among figures, it is circles, and among bodies, the heavens, that are considered the most perfect. However, when experience is seen to teach something different to those who pay careful attention, namely, that the planets deviate from simple circular paths, it gives rise to a powerful sense of wonder, which at length drives men to look into causes.
Now, the looking into causes is what the oligarchy feared the most. But this is what the Greek scientists, as described by Plato, Eratosthenes, and Archimedes, and the others, did. They looked into the causes, and they began to unravel these complicated motions with their minds, and were able to see with their minds how God ordered the solar system. But after the murder of Archimedes by the Romans, this effort to look into the causes was suppressed. I'd like John to read a quote from Ptolemy, which describes exactly how he thought about this.
For indeed, Aristotle quite properly divides the theoretical into three immediate genera: the physical, the mathematical, and the theological. The theological and physical genera are expounded in terms of conjecture, rather than in terms of scientific understanding. The theological, because it is in no way phenomenal and attainable, but the physical, because its matter is unstable and obscure. For this reason, philosophers could never hope to agree on them. And mediating that, only the mathematical, if approached inquiringly, would give its practitioners certain and trustworthy knowledge with demonstration both arithmetic and geometric, resulting from indisputable procedures we were led to cultivate most particularly, as far as lay in our power, this theoretical discipline.
This is the kind of science that suits the oligarchs the best. No knowledge of God is possible. No knowledge of the physical universe is possible. But mathematical knowledge is attainable. And of course, only mathematicians can master this knowledge. And so you have a priest class of spooks who can manipulate the equations and the formulas to interpret for us the motions of the planets. But for us, for everyone else, this is the world, according to Ptolemy. The Earth is at the center. All the planets move around the Earth, including the sun, in perfect circles, with the stars staying in the same positions relative to each other, the fixed stars, without moving. Now, and this never changes. In fact, of course, this has a certain appeal to naive sense perception because from the standpoint of what you see, you don't see anything other than what disappears. You see the stars moving and the planets and the sun moving about you in what appears to be perfect circles. Unless, as Kepler says, you look at it closer and then you get this degree of wonder which provokes you to look into the causes. Now, the problem with this, while this is a useful bit of image for the illiterate, ignorant majority of a population in a feudalistic society, a slave society, it isn't very good even for the mathematicians. Because if you were to take this as the physical construction of the solar system, you would not be able to predict or to understand what the motions of the planets were. And so Ptolemy, in order to keep from being discredited, had to come up with a complicated set of formulations in order to account for the irregular motions of the planets that we observe, which do not derive from this fixed model. So for the masses of the people, this is the world. That's all you need to know. And for the mathematicians, we have a complicated construction, which I'll illustrate with the next animation. Okay, this is the Ptolemaic system of epicycles. The center is the stationary Earth. The blue circle is a circle of which the Earth is the center. The red dot is the planet. The planet is moving on this smaller blue circle, whose center is moving along the larger blue circle. As it moves, as the planet moves along in that configuration, the path of the planet that the planet traces out around the Earth is the red circle, which brings it closer to the Earth at the bottom of its orbit, farther from the Earth, an observer at the Earth at the top of its orbit. So it would appear to move faster here and slower there. And it would appear to be speeding up and appear to be slowing down. And at the top of the orbit, if you notice, the little blue circle is moving counterclockwise, and the planet is moving clockwise, which gives the appearance of retrograde motion. Now remember that Ptolemy did not say this is the way the planets moved. The planets were in the fixed order that he said. But this was the means by which the complicated motions were calculated. What's most important about this is not simply that it is somewhat convoluted, but that it calculates the non-uniform motion, the observed non-uniform motion of the planet as the result of a compilation of circular action, and only circular action and nothing else. And as the years progressed, the ability of this kind of formulation to even cohere with the actual observations became less and less, and the system became completely discredited. But in the Renaissance, there was a major breakthrough done, largely sparked by the work of Nicholas of Cusa, who recognized that the world doesn't work in perfect circles, that God created the universe in such a way that the perfect circle is only the image of God, and that in the physical world there are no perfect circles. And as Cusa said it in his famous book In Learned Ignorance,
"Wherefore it follows that except for God, all positible things differ. Therefore, one motion cannot be equal to another, nor can one motion be the measure of another, since necessarily the measure and the thing measured differ. Although these points will be of use to you regarding an infinite number of things, nevertheless, if you transfer them to astronomy, you will recognize that the art of calculating lacks precision, since it presupposes that the motion of all the other planets can be measured by reference to the motion of the sun. Even the ordering of the heavens with respect to whatever kind of place, or with respect to the risings and settings of the constellations, or to the elevation of a pole, and to things having to do with these, is not precisely knowable. And since no two places agree precisely in time and setting, it is evident that judgments about the stars are, in their specificity, far from precise. But it is necessary that every part of the sky be moved, even though the parts are moved unequally by comparison with the circles described by the motions of the stars. And there is not a star which fails to describe an approximate circle. And we are surprised when we do not find that the stars are in their right position according to the rules of measurements of the ancients. From the foregoing considerations, it is evident that the earth is moved.
Now you see that Cusa has launched a revolution which strikes terror in the hearts of an Aristotelian. Because in the world as Cusa describes it, the universe, the non-uniform motion of the planets is not an appearance, not just an illusion, but is the way the universe is constructed. But in such a universe, precise calculation is impossible. This creates the crisis that today you see come up in things like benchmarking, or the reliance on computer benchmarking, or economic models of forecasting, or whatever, where you have a conflict between the way the world is and precise calculation. At that point, you have to make a decision. Do you search for the truth, or do you make the world bend to what is susceptible to your mathematical calculations? And this launched the revolution which overthrew the Aristotelian and the Ptolemaic system. And in fact, Kepler himself was a great follower of Cousin and quotes Cousin frequently in his works. Now let's go to the next slide. After, as Ptolemy's system began to crumble, some other systems or configurations of the solar system began to be developed. This is the system of Tycho Brahe, who was a Danish astronomer who later led the observatory in Prague at which Kepler worked. Kepler depended on Tycho Brahe for his observations. Tycho Brahe was known for his tremendous skill in making precise measurements of the motions of the planets. Brahe rejected the Ptolemaic system and replaced it with this one, where the Earth is at the center, but all the planets move about the sun. And that configuration moves about the Earth in a circular path. Now, Brahe also, you'll notice there's a little comment there. Brahe made a major step in overthrowing the Ptolemaic system because in Ptolemy's system, to keep the planets moving in these circular paths, he envisioned the world being a series of concentric solid orbs, transparent spheres, and that the planets moved in tracks along those orbs, and that the speeding up and slowing down of the planets in those tracks was a result of demigods which controlled the motion of the planets. And that is, the demigods sped up and slowed down, these lesser intelligences, which of course everybody had to propitiate. And Brahe demonstrated that the comets actually traversed an orbit which crossed the paths of the planets, which meant that there couldn't be solid orbs. And so the Ptolemaic system collapsed. And go to the next one. This is the other major configuration, which of course you're known to you, is called the Copernican system, in which the sun is at the center and all the planets, including the Earth, rotate around the sun. And the Earth rotates in the third position around the sun. Now, this system, we should dispel a commonly accepted myth, which is taught in most schools today, that Copernicus somehow made a revolution. Not true. This system is actually the oldest one. Aristarchus had already discovered the idea of the heliocentric solar system. And as you heard Cousin, more than 100 years earlier, said the Earth is moved. So Copernicus simply goes back to the oldest system, the Aristarchan system. But unlike the Greeks, Copernicus and Tycho Brahe made exactly the same error that Ptolemy did. And this is what Kepler pointed out. And that error was to believe or to insist that the actual motion of the planets, the physical causes, the true physical causes, was unknowable. It was only mathematically knowable. The one immediate advantage of the Copernican system, we'll see in the next animation, is that if you have the Earth moving, then those loop-de-loops that you saw with the planets results from the appearance that happens when the planet, the Earth, as an inner planet, passes the orbit of the outer planet. Now, this is just a depiction. This is not an actual Copernican orbit. But if you think of the sun at the center, the inner blue circle as being the orbit of the Earth, and the outer blue circle as being the orbit of, say, Mars, you'll see that as this goes around, at the top of the orbit, when the inner planet passes the outer planet, an observer on the inner planet would see the outer planet move backwards. See that? So the retrograde motion, the loop-de-loop, according to the Copernican system, is resolved by putting the Earth in motion. However, what's not resolved is the issue of the non-uniform motion. And the question that Kepler pointed out, that all three of these examples, these systems, rely on perfect circles. And in fact, Kepler pointed out that here you have three radically different systems: the Ptolemaic system, the system of Tycho Brahe, and the system of Copernicus. Completely different. And yet, when it comes to looking at their predictions relative to the observations in the sky, the results are the same within a hair's breadth. So if three different systems give you the same result, and all three systems say these are only mathematical systems, how can you tell which is true and which is not? Why believe Ptolemy over Copernicus? Why believe Copernicus over Tycho Brahe? Why believe any of them? There's absolutely no way to know which one is true. And in the new astronomy, Kepler, this is the basis on which Kepler wrote his book, The New Astronomy, which develops the new revolution in astronomy that he made. And John will read the statement by Kepler.
My aim in the present work is chiefly to reform astronomical theory, especially of the motion of Mars, in all three forms of hypotheses, so that our computations from the tables correspond to the celestial phenomena. Hitherto, it has not been possible to do this with sufficient certainty. In fact, in August 1608, Mars was a little less than 4 degrees beyond the position given by calculation from the Prutenic tables. In August and September of 1593, this error was a little less than 5 degrees, while in my new calculation, the error is entirely suppressed. The eventual result of this consideration is the formulation of very clear arguments showing that only Copernicus's opinion concerning the world, with a few small changes, is true, that the other two accounts are false, and so on. Indeed, all things are so interconnected, involved, and intertwined with one another that after trying many different approaches to the reform of astronomical calculations, some well trodden by the ancients, and others constructed in emulation of them and by their example, none other could succeed than the one founded upon the motion's physical causes themselves, which I establish in this work.
When Kepler says the Copernican system is the true one, he is saying something Copernicus himself was afraid to say. And also that had never been said before, that brought us the 1500 years of the Dark Ages, in which the looking into the true causes was not allowed. He brought that back to light. Now, the key problem Kepler had to confront here is the one that Cousin raised, which is the question of non-uniform motion. Because as Cousin says, in non-uniform motion, the problem is that you can know the position of the planet, but it's not precisely calculable. Now, to get a sense of this, let's look at the next two animations. This animation is uniform motion. The moving dot moves around the stationary dot at a uniform rate in a perfect circle. Now, as it moves, I'd ask you to look at two things. First of all, the fact that once it starts moving and establishes its course, it doesn't have to change. It does nothing different from moment to moment. All it has to do is stay the same position, the same distance from the stationary dot, and keep itself at 90 degrees from a line connecting the two. Each moment is the same as the moment before. The motion today, the motion in each moment is the same as it was and the same as it will be. Again and again and again. Nothing has to change. Now also think about this. An observer on the moving dot would see the stationary dot move in uniform motion. An observer on the stationary dot sees the moving dot moving. So from a mathematical standpoint, from the standpoint of sense perception, there is no way to know which is moving and which is not. Now let's go to the next one, and you'll see how what kinds of questions are raised by the problem of non-uniform motion. Now here the red dot will move around the orange dot in a non-uniform way. It will change its speed, it will change its direction, and it will change its distance to the stationary dot at every moment. Every moment is different than the one before and different than the one that will come. And you'll see it speeds up and slows down. So the question that's raised by this is, how would the moving dot know to stay on that path? How does it change its action at each moment, from moment to moment, so that it traverses that path again and again and again? Whereas the planets in uniform motion require no change, this requires a process that is congruent with cognition. Now, again, though, if you were an observer on the moving dot, you would see the stationary dot move around you in non-uniform motion. Same problem, except that you'd see the non-uniform motion. And if you're on the stationary dot, you would see the moving dot move. Now, so you still have this problem, that from the standpoint of pure mathematics, there's no way to tell which one is moving. So Kepler didn't ask what is moving. He asked, what is the mover? What is the physical causes? And he developed the hypothesis that the sun was the mover, that the sun had a virtue, and that virtue extended throughout space. And that virtue, the effect of that virtue, diminished with the distance from the sun, and it was that virtue which was moving the planets. This virtue was akin to a magnetic force, as described by the English scientist Gilbert. And if the planets were moving in a path that took them farther and closer to the sun as they moved around it, they would be in a state of increasing or decreasing effect of the sun's virtue. And that would physically account for the speeding up and the slowing down of the planet's motion around the sun. Now let's go to the next one. This is Kepler's first approximation of such an orbit, that the planet was moving on a circle about the sun, but the sun was not at the center of the circle. The sun was at some eccentric point, and that the planet moved still on a circle, but in such a way that it brought it closer and farther to the sun as it went around. You'll notice that that as the line from the sun to the planet gets shorter, the planet speeds up, and as it gets farther away, the planet starts to slow down. Now, here's where Kepler ran into the problem that Cousin describes as having the motions of the stars not being susceptible to precise calculation. Because if you think of an entire circuit as one period, the total elapsed time of the planet going around one orbit, that is not time on your watch, but time as one orbit, that the planet would move, if you tried to divide that up into portions, it would move smaller distance in the farther regions of its orbit than in the closer regions of its orbit. So you could not divide the planet's period into equal portions by dividing the arcs. It was not susceptible to precise calculation. So go to the next animation, and you'll see how Kepler developed a means to measure that precise, to measure this non-uniform motion, which was not to measure the distance the planet traveled along the arc, but to measure the area swept out by the planet as it moved. that is the area from the sun, a line connecting it to the planet, which is this yellow line, an arc, the green arc, and this blue line. That region, that area, was the measurement of time. And that those portions of the planet's orbit, which were equal in area, were equal parts of the planet's period. Now stop the animation when the planet gets to about 2 o'clock, right there. And you'll see the problem of not being able to precisely calculate this. That circular area for the motion of the planet, say from this point up to where it is measured by this area, the area bounded by the yellow line, the green arc, and the blue line. But that's not a portion of the circle. That area is equal to this portion of the circle, that is the orange, bounded by the orange line, the green arc, and the blue line, plus this triangle, the yellow line, the orange line, and the blue line, plus that little triangle. Those two segments make up the orbit, make up the area. However, the area of the triangle is equal to 1/2 this distance, the base, times this length here, the height, and that height is the sine, called the sine of this angle. Now, the reason why that's a problem is that the sine is non-uniform relative to the angle. This is what Caucus discovered as the incommensurability between the straight line and the arc. Now run the animation again, and what I'd ask you to watch is watch the relationship between that orange line and the angle formed by the orange line going from the center of the circle to the planet. You'll see that the vertical line grows at a non-uniform rate with respect to that angle. In other words, when that angle, when the planet reaches, say, half the distance from here to 90 degrees, the sine has gone up nearly 3/4 of its length. And it goes only 1/4 of its length in the second half of the orbit. So the mathematical representation that Kepler discovered embodies the very problem that non-uniform motion creates. And so this created a whole new problem, a problem that led Kepler to call for the development of the calculus. Now, just to state this problem in the terms that Kepler did, if you think of the time elapsed as the area swept out, that is, if I know where the planet is, if the planet moves from here to here, I can tell you how much time elapsed, what portion of the period has been elapsed in that period of time. But because of the heterogeneity of the sine and the angle, Kepler cannot answer the question, how much time will be elapsed when the planet gets to another position? Or inversely, where will the planet be when an equal amount of time will be elapsed? In other words, the past was calculable. The future was knowable, but not calculable. That is the problem that led Kepler to call for what Leibniz later developed was the calculus.
It is enough for me to believe that I could not solve this a priori, owing to the heterogeneity of the arc and the sine. Anyone who shows me my error and points the way will be, for me, the great Apollonius.
Now, anybody who tells you that there's any other source to the calculus is wrong. Now, after developing this concept, Kepler then applied his results to Tycho Brahe's observations. And he found that after 79 efforts, he had a serious failure. Every single effort was off by about 8 minutes of an arc. Now, just so you understand what that means, there are 360 degrees in a circle and there's 60 minutes in an arc. That's a very small amount. An amount that could easily could have been written off as an error in measurement. But Kepler didn't see it that way. He saw it as a matter of principle, and caused him to come up to scrap his hard-won discovery and provoke him to develop a new one. And he describes in the New Astronomy the subjective process that he went through in order to deal with this, in order to give up what he had already discovered for what he knew to be the truth.
While I am thus calculating a triumph over the motions of Mars and fetter him in the prison of tables and the leg irons of eccentric equations, considering him utterly defeated, it is announced again in various places that the victory is futile and war is breaking out again in full force. For while the enemy was in the house as a captive and hence highly esteemed, he burst all the chains of the equations and broke out of the prison of the tables. Outdoors, meanwhile, spies, positioned throughout the whole circuit of the eccentric, I mean the true distances, have overthrown my entire supply of physical causes, called forth from chapter 45, and have shaken off their yoke, retaking their liberty. And now there is not much to prevent the fugitive enemy from joining forces with his fellow rebels and reducing me to desperation, unless I send new reinforcements of physical reasoning in a hurry to the scattered troops and the old stragglers, and informed with all diligence, stick to the trail without delay in the direction whither the captive has fled. In the following chapters, I shall be telling of both these campaigns in the order in which they were waged. Galatea seeks me mischievously, the lusty wench. She flees the willows, but hopes I'll see her first. It is perfectly fitting that I borrow Virgil's voice to sing this about nature. For the closer the approach to her, the more petulant her games become, and the more she again and again sneaks out of the seeker's grasp, just when he is about to seize her through some circuitous route. Nevertheless, she never ceases to invite me to seize her, as though delighting in my mistakes.
Why don't we bring up the next animation, which you'll see how Kepler solved this problem. You'll understand Kepler's metaphor, by the way, a little bit easier if you remember that the Mars was the name of the Greek god of war, and he was living in a period at a time in which was the beginning of the 30 Years' War. Now, what Kepler did was to abandon the idea of the circular orbit and to recognize that the planet was moving not on a circle, but around an ellipse. And this is the blue ellipse is the elliptical orbit. The green circle is where the planet would be if it were on a circle, and the white dot moving around is the uniform motion. So what you see here is the planet is the red dot moving on the blue ellipse. The green dot is moving on the green circle is where the planet would be moving, where it's still on a circle, and the white dot is the uniform motion. So when the planet is in the upper part of its orbit, it's moving slower than uniform motion, and when it's moving in the bottom part, it's moving faster than uniform motion, and all three come together at the two extreme points. And this is a development of Kepler's idea of the elliptical orbits. Let's go to the next one. This is Kepler's drawing of the elliptical orbit straight out of the New Astronomy. Next one. So Kepler developed a hypothesis, a physical hypothesis that showed the harmonic ordering principle of the entire solar system. And that hypothesis is what Gauss and Riemann would later call a hypergeometric function. The hypothesis that the solar system was organized in such a way that the number of planets and their spacings was determined by an ordering principle of the 5 Platonic solids inscribed and circumscribed in perfect spheres. Next one. That the equal portions of the planet's orbit corresponded to equal areas, not equal arcs. Next one. That the planets had a relationship to each other such that the distance of the planet to the sun and the total time that it took the planet to elapse, the ratio of those two things was proportional for all the planets. Next one. and that if you took the slowest speed and the fastest speed of each planet and compared them to each other, that they formed musical intervals that were harmonic intervals, and that these harmonic principles were present at every moment of becoming of the planet's action, and that was how non-uniform motion was characterized as an actual physical process in the universe. Next one. And that Kepler describes that you have a relationship between the sun and each planet individually, and the sun and all the planets, which he compared to Plato's idea of reason to understanding, or Kuza's idea of mind to unfolded mind, and that there was a dissonance in this whole thing, a dissonant interval, which was the distance occurred between the distance between Mars and Jupiter, in which Kepler said that there must be something there, probably an exploded planet, which has yet to be discovered. Let me interrupt at this point to present another example of non-uniform physical action, which at first may seem far distant from planetary orbits, but is actually closely connected to them. This is a picture of a laser beam passing through the air and being reflected by a mirror. If you were to measure it carefully, you would see that the angle at which the light strikes the mirror, which is called the angle of incidence, is equal to the angle at which the light leaves the mirror, which is called the angle of refraction. Here is a picture of the same laser striking the mirror at a different angle. Here is still another angle. In each case, the angle of incidence and the angle of reflection are equal. In this animation, the red lines represent the laser light and the horizontal yellow line represents the mirror. As this animation illustrates, for every change in the angle of incidence, the angle of reflection changes in exactly the same way, that is, uniformly. However, this demonstration only describes what we observe. It doesn't consider, as Kepler would, the true physical causes underlying the phenomena. This phenomena had been measured by the scientists of classical Greece. However, the followers of Plato at the Academy of Athens were not merely concerned with describing observed phenomena. Rather, they sought to discover the underlying principles that governed such phenomena. These scientists determined that the angle of incidence and the angle of reflection of light were equal because when these angles were equal, the total path that the light took was the shortest distance. This they understood to be a reflection of a universal principle that nature always seeks the shortest path. Now look at a different phenomenon of light. Here is a picture of the same laser traveling first through the air and then into oil. Notice how the light bends at the boundary between the air and the oil. Here is another picture of the laser striking the oil at a different angle. And here still another angle. This phenomena, called refraction, is paradoxical with what we just discovered concerning reflection. The angle of incidence in refraction is not equal to the angle of refraction. And furthermore, the angle of incidence and the angle of refraction change non-uniformly. This is illustrated in this animation. The horizontal yellow line represents the boundary between the air and the oil, and the red line on the top represents the laser going through the air, and the red line on the bottom represents the laser in the oil. Notice that as the angle of incidence changes, the angle of refraction also changes, but not in the same way. As the angle of incidence gets steeper, the angle of refraction also steepens, but slowly at first, then faster and faster. Kepler and some of his contemporaries, like the Dutch astronomer Willebrord Snell, discovered the relationship between these angles. In this animation, those signs are represented by the horizontal green lines. In other words, even though the angles change non-uniformly, the signs are always in proportion. This is another example of Cousé's principle that motion in the physical universe, or action in the physical universe, is non-uniform. And owing to the heterogeneity of the arc and the sine, it is not precisely calculable. But refraction represents another paradox with respect to reflection. In the case of reflection, light traveled along the shortest path. But in refraction, light does not travel the shortest path. As you can see in this picture, the shortest path is represented by the dotted line. Thus, refraction seems to contradict the concept that nature always takes the shortest path. It was Pierre de Fermat, who lived right after Kepler, who determined the solution to this paradox between reflection and refraction by investigating the real physical causes of refraction. Fermat determined that the reason why the angles of incidence of an angle of refraction varied according to the signs was because the light was actually slowing down when it shifted from motion in air to motion in the denser medium in the oil. Therefore, the light was not seeking the shortest distance, but the light had to find the path of least time. Now, look back at reflection. There, the light was always traveling through air, and thus its speed was unchanged. Therefore, in reflection, the path of least time is the same as the shortest distance. But when light is refracted, it slows down. And these two paths are not the same. Here, for nature to find the shortest path, it is the path of least time, not shortest distance. This demonstrates that the universe does not conform to the axioms, postulates, and definitions of Euclidean geometry, and that we must abandon such preconceptions for what Riemann would later develop as a relativistic conception of space-time. This raises the same questions as Kepler's discovery of the non-uniform motion of the planets. How does the light know how to find the path of least time? How does the planet know how to change its speed and trajectory at each moment in order to find the elliptical orbit? The only answer is that cognition is a universal principle. The planet, or the light, acts according to the principle of mind because the universe is dominated by the principle of cognition. Now let's return to the live presentation that I made at the Schiller conference in February of 2001. To solve these kinds of problems required the development of a new idea of geometry of position, in which the position of the planet or the light or any other physical body is dependent not on some other position, but on a process of change. And that process of change corresponds not to simple numbers, but corresponds to incommensurable magnitudes. This is what is at the basis of Leibniz's development of the calculus. And if anybody tells you anything different, it's just a fraud. And in fact, the fraud that you were taught, what you're taught in most schools today, is in fact a fraud. The oligarchy wanted to destroy this idea, and they hired the next man, Isaac Newton, who was a certified lunatic, pervert, alchemist, who replaced Kepler's idea of ellipses and non-uniform motions with straight lines and stole Leibniz's calculus. And in fact, none of Newton's theories were original. They were simply just algebraic derivations of what had already been developed by Kepler and Leibniz. He put in effect the shroud of Ptolemy, the idea of mathematical formalism to replace physical causes. He put that back into science. And the oligarchy defended Newton and intimidated anybody who stood in his way. The most notable exception of this was a man named Abraham Gotthelf Kästner. Kästner was a scientist who lived from 1714 to 1801. He was born in Leipzig at the time when Johann Sebastian Bach was there. He later became a professor at Göttingen University. He was the host of Benjamin Franklin when Franklin came to visit Göttingen. He was the teacher of Lessing. He was also the teacher of Gauss. He was a poet, and he was a passionate defender of Kepler and Leibniz. And he wrote a history of mathematics in which he asserts in there, which is largely suppressed, in which he asserts in there the truth, that it was Kepler who discovered the harmonies of the planets, not Newton. To give you a sense of Kessner's wit, as I said, he was a poet, and he wrote epigrams, one of which was dedicated, several of which were dedicated to Kepler. I'd like John to read one of them.
No mortal climbed as high as Kepler climbed, and died in need, unfed. He only knew to please the minds, and so the bodies left him without bread.
Now, aside from Kessner, Newton's hoax achieved ascendancy until 1801. Go to the next slide. This is what the sky looked from Sicily on January 1st, 1801, the first day of the new century. Giuseppe Piazzi, an Italian astronomer, was looking at the sky, and he saw, go to the next slide, this, a tiny dot, which he had never seen before. And that dot moved relative to the fixed stars. Go to the next one. So about 11 days later, it was here and then there. Then it disappeared from view. And this presented a challenge to every authority in science. How, from that very small interval of the planet's orbit, could that planet be rediscovered? Could the orbit of that planet be known so that it could be reobserved in the sky? For several months, every authority in Europe looked for Ceres using Newton's method, and they failed. In August of that year, for the first time, Piazzi's observations were made public outside of the immediate circle of scientific authorities. And a 24-year-old mathematician named Carl Friedrich Gauss, a student of Kessner, took those observations and, using Kepler's method, determined the orbit of Ceres. And based on that orbit, he told the world, you can see Ceres if you look in the following place. Where Gauss was telling people to look was a far different place than where all the authorities were telling people to look. And you couldn't look two places at once. You could either go with the authorities or you could go with Gauss. On the first clear night, those who went with Gauss saw Ceres. Those who went with Newton saw nothing. Several years later, this obviously made not only Kepler proved Kepler right, but it made Gauss very famous. And several years later, he was appointed to be the head of the observatory at Göttingen University. And in that capacity, he gave a speech in which he described why it is necessary to study astronomy.
As the prologue of any science is transmitted, one also becomes concerned with the question, what use is this science? This is no better sign of the spirit of the times when one hears such a question often and always thrown up again. It speaks of an unfortunate misunderstanding between necessity, or the necessity for the obligatory requirements of life, and the resources to fulfill those requirements. It is a silent confession of a truly ignoble degree of dependence on those requirements if one believes that everything must be to procure our physical needs, if one demands a justification for occupation with science and cannot conceive that there are people who study because for them study itself is a necessity. But to judge in this way documents not only our poverty, but at the same time it shows a littleness, a narrow and sorry way of thinking, a disposition always to anxiously calculate the reward before any effort, and an indifference and lack of feeling toward the great and the nobility of man. One can unfortunately not deny that such a mode of thinking is not uncommon in our age, and I am convinced that this is closely connected with the catastrophes which have befallen many countries in recent times. Understand me correctly. I do not speak of the general lack of concern for science, but of the source from which all this flows, of the tendency to everywhere look out for one's advantage and to relate everything to one's physical well-being, of the indifference towards great ideas, of the aversion to any effort which derives from pure enthusiasm for the thing itself. I believe that such attitudes, if they prevail, can be decisive in catastrophes of the kind we have experienced.
About 40 years after Gauss made that speech, John Quincy Adams, former President of the United States, who was then a congressman, traveled to Cincinnati to lay the cornerstone in the first astronomical observatory in the U.S. And he gave an address in which he referred to the connection between the principles of astronomy and the Declaration of Independence, that the inalienable rights, the rights to life, liberty, and the pursuit of happiness, especially the pursuit of happiness, are rights which come from nature's God, rights which are written in the stars themselves. And that it was our nation's commitment to those rights that differentiated us from the British Empire. And he outlined in that speech a mission for the United States, which is enunciated at the end of the speech.
We have been sensible of our obligation to maintain the character of a civilized, intellectual, and spirited nation. We have been, perhaps, over-boastful of our freedom and oversensitive to the censure of our neighbors. The arts and sciences which we have pursued with most intense interest and persevering energy have been those most adapted to our own condition. We have explored the seas and fathomed the depths of the ocean, and we have fertilized the face of the land. We, you have converted the wilderness into a garden and opened a paradise upon the wild. But have not the labors of our hands and the aspirations of our hearts been so absorbed in toils upon this terraqueous globe as to overlook its indissoluble connection, to even physical, with the firmament above? Have we been of that family of the wise man who, when asked where his country lies, points like Anaxagoras with his finger to the heavens?
Let's have the last slide. This is the asteroid Eros. It's a neighbor to Gauss's Ceres and a part of Kepler's missing planet. Last week, human cognition touched this asteroid when an artificial probe landed on its surface. However, this achievement is but a small flicker of the mission enunciated in John Quincy Adams' address, the which was carried forth by Abraham Lincoln, Franklin Roosevelt, and John F. Kennedy, who called on us to do not what is easy, but what is hard. For more than 3 decades now, Lyndon LaRouche has called us to an even greater mission: to transform the underdeveloped regions of our planet, to explore and colonize Mars, the solar system, and beyond, and to create the cultural conditions that will make that happen. As LaRouche once wrote, to reach out with our thoughts and bend the stars like reeds. Therefore, let us continue the journey we've begun here today by dedicating ourselves fully to that mission, committing ourselves to do what it takes to lift the shroud of ignorance that has fallen on our fellow man and restore to them their mind's vision, so that all people on this earth will, like Anaxagoras, find their country in the heavens. Thank you for your attention.